Good morning, Dr. Iza. We are from Group Parallel Guys. Today we are going to presentation about our project 2 ALU design. So my name is Edward Poetet.
My name is Bang Biaoxian.
My name is Toh Yihong.
Now I will like shortly briefing our introduction of RSCV. RSCV is a reduced instruction set computing which is highly regarded in instruction set architecture ISA, which is used for simplicity, efficiency, and high performance. Inside the RSCV, we got arithmetic logic unit ALU, and in this project we are going to design an ALU using the adder, multiplexer, and register. So this is the top level block diagram of the ALU design. In this part, we are going to divide into three phases, which is 4-bit, first phase 4-bit 4 to 1 multiplexer, second phase 4-bit ripple carry adder, and third phase register, which is using the 4-bit flip-flop. And the input is using the 4-bit, selector is 2-bit, and the else input is using the 1-bit. Next.
Right now I'm going to talk about single 1-bit 4x1 multiplexer. Selector, they have two selectors to select which bit is output, and this is the Boolean algebra of the circuit, which is when SL1 and SL0 is 0, you will select A0, which is, and so on. It's the symbol of the circuit just now, which is a 1-bit multiplexer that select each bit from each digit of those inputs. And then we have two selectors, which connect to every single multiplexer. And then we have 4 buses which contain 4 bits, and output buses which contain 4 bits as well. As you can see, the first multiplexer will connect to A0, 0, and A1, 0, and A2, 0, and A3, 0, which of is every buses of the first bit of every buses. And this is our A and B 4 bits 4x1 multiplexer, and we create two symbols which of the circuit just now for A and B multiplexer. And we have sector A and sector B, and we have 4 A and B buses which contain 4 bits each, and then we output 4 A and B output buses which contain 4 bits each as well. And it's a waveform result for A and B 4 bits or 4x1 multiplexer. As you can see, when the SL is 0, 0, the out is 0, 0, 1, 1, which is correct because it's A0. And when the B cell is 1, 0, the B out is 1, 1, 0, 1, which is correct because it's a value of P2. After we done analysis and synthesis, we create a new university program VWF file. We create a symbol from the block 2, and then this is our A and B 4 times 1 multiplexer circuit. And then we set the hierarchy as a top level entity, and then run the analysis. As you can see, the result is correct. When I set out 0, 0, which the output is A0, and 0, 0, 1, the output is B1.
Next, I will introduce about the logic circuit for our single vote adder. The A input and B input is actually get from the 4-bit 4-bar multiplexer previously, and the C input is the ALU op in our assignment. So after we design our logic circuit, the Boolean expression for our S output is A XOR B XOR C, and the Boolean expression for our C output is A and B or B and C or A and C. So for the 4-bit ripple carry adder, these 4 symbols is the single vote adder that we created recently, and the line with the thicker wave is the bus that can carry multiple inputs at a time. So the C out of previous single foot adder is the C in of the next single foot adder. Next, to make it function as an adder or a subtractor, we need XOR gate. So the reason for me to not put the XOR gate in the foot adder previously is because in our assignment we are required to minimize the usage of logic gates. And if I add the XOR gate here, I will need 4 XOR gates. But in my case, I only need 1. Next, a NOT gate is added here so that the RCA can act as adder when ALU op equals to 1 and subtractor when ALU op equals to 0. Next, in quarters, this is the logic circuit for single full adder, and this is the symbol for our single full adder and the whole logic circuit for full adder. This is a symbol for full adder, and the whole logic circuit is for adder or subtractor. After simulate the waveform result, this is our waveform result when ALU op equals to 0, and this is the result when ALU op equals to 1.
And for the register, the D-in is contains 4 bits and it has buses for the output and the D-in, and which connect to every single D flip-flop and the clock and reset as well. The input is got from the full adder as well. And this is the waveform result for 4 bits D flip-flop when ALU op is equal to 0. And this is a waveform result for 4 bits D flip-flop when ALU op is 1. As you can see, the ALU op when the reset is high, the clock is high, the result will be stored. And when the ALU op is 1, no single ALU out will always be 0. When reset equals 0, the ALU out output 0 immediately. This shows the result. The reset is asynchronous with the clock. This is our D flip-flop register, and it's parallel in and parallel out. And then we have D in, which contains 4 bits, and then clock and reset as well. And let's run the simulation from that. If the reset and the clock is 1 at the same time, the ALU out will be 0, 1, 1, 1. And if the clock and the reset is not in the same voltage level, and when the clock is 1, the reset 0, the output will also be 0. And that's correct.
Next, this is the overall ALU design circuit. So, which is the combination of the three phases, which is the multiplexer, adder, and the register, which is the D flip-flop. This is the waveform from when ALU up is equal to 0, and this is the waveform when ALU up equal to 1. So, for our conclusion, our accomplishment is this assignment is to for efficient design, comprehensive implementation, verification, and validation of our circuit and educational value. That's all for us. Thank you.